Okay. So yeah, here's the agenda. It's very simple. I'll have two parts as a general, and then we'll dive into the AutoGen framework. For both parts, there are two big motivating questions I want to cover. Number one is, what are the future AI applications like? And then number two is, how do we empower every developer to build them? So let's start with the first question. What are the future AI applications like? So starting from around the year like 2022, we see the big power of the language models and other generative models. So the generative AI, people have seen a superior capability of generating content like text and images. They are much better than the generative techniques like 20 years ago or 15 years ago, where I was doing my PhD and study like topic modeling and other older generative modeling techniques. Apparently, these days, the new technique has passed the bar that we can think about in more creative applications, higher level of AI capabilities. And so what's the next? What are the best way to leverage these generative AI techniques? So starting from early last year, we started to think about that question, and we made a lot of technical bets along the way. The most important bet would be that we think the future AI applications can be agentic, and the agents can be a new way for human to interact with the digital world and help us execute more complex tasks on behalf of human and get to higher and higher level of complexity. We got a lot, at that time, many people still have doubts about whether agentic AI can be a viable notion. But as time goes by, we are seeing more and more confirmation and evidence, including earlier this year, there's an article published by Berkeley talking about how we're observing more and more AI results shifting from using a simple language model to building compound AI systems. So that's one of the similar observations and technical bets we made. So if we think about the examples of agentic AI, you'll notice that building AI agents like personal assistants, autonomous bots, or gaming agents, there's the notion of agent AI is not new. But what's new is that with the power of the new generative AI techniques and the language models, for example, we're able to build some of the old agentic applications much easier and much more capable. And at the same time, we're also seeing some very new, novel agentic applications that go beyond the imagination we had before, such as some science agents that can do science discovery automatically, web agents that can automate some web browsing and web automation tasks, and also software agents that can build even software from beginning to scratch. I bet you have seen a lot of demos before, but today let me show you a very recent demo. I just got this morning from a startup called Zinli. This is an example of building a website to extract the models from Hugging Face and download automatically. So after you give the request to the AI, they started working on them automatically, starting from analyzing the task, looking for information, and installing the necessary dependencies. They do use a multi-agent framework to have agents of different roles to finish the task and can do multi-step of tasks. Now we're seeing that AI is creating different files. All the reasoning and between the agents are done automatically using both language models and tools. So agents are talking to each other now. They are developing the website. And finally, they are trying to build and compile the website. Okay, here we go. This is a website built by the AI. It looks like functioning. There are many models already listed in the website, and users can search model and export model data and download the data, download the models. it looks like the video is playing in the slower speed than normal. I'm not sure if that's because of the internet issue. And furthermore, if you happen to make some mistakes, for example, if you remove the very critical line of code from the files that are already created, let's see what happens. So we are running the AI again for executing the same task. So this time the AI is able to, it's trying to also perform the same task. But because of that remove of the critical lines of code, we're supposed to hit some error. Yeah, so we see an error message there. It's missing script. So let's see what AI will do. So just within a few steps, the AI is able to correct the mistake and finish the exact line we just removed. So complete the task. So that shows some self-healing and self-recovery ability of AI agents. So hope that to give us an idea about the potential kind of promise the AI agents can give us. In future, we may build the software in a totally different way. So to summarize the key benefits of Agentic AI, number one is many people understand that AI is able to use a more natural interface to talk with humans, so you can tell them what you want exactly. In this case, you just tell them we want to build a website with certain requirements, and then you can iterate over the natural language. And also by giving the agents more capabilities, they are able to operate and finish more complex tasks with minimal human supervision. So that has tremendous value in terms of automation. And the third point, I think it's less talked about among people, but I have a strong emphasis. That is, agentic AIs can be also a very useful software architecture to enable us to build software in a totally different way, so that you can have multiple agents working with each other and to finish much more tasks in a recursive way. So I will use a simple example to go over these benefits. So let's look at one particular example application about solving some supply chain optimization on cloud. This application is built by my former colleague from Microsoft Research. It allows users like coffee shop owners to answer questions like, what if we change the shipping constraints? How would that affect my operating cost? So this is a difficult question. They can't get answers from like ChatGPT because the AI needs to understand the user-specific data, constraints, and even some optimization tools to be able to understand the question and get the answer. But with in this case, they use AutoGen to build 3 agents that can solve this question very nicely. The 3 agents are commander, writer, and safeguard. So let's see how that works. So initially, the user sends a question. What if we prohibit shipping from supply 1 to roastery 2? The commander receives that question. Before it tries to answer that question, it will hold the current conversation and initiate another message chat between the commander and the writer. The writer in this case is using a large language model as a backend, try to understand the question and proposes some code that can be used to answer this question. In this case, it suggests some Python code of adding a specific constraint into the optimization problem, and returns that code to a commander. The commander sees that code, again, it holds the conversation with writer and starts another message chat between the commander and safeguard. The safeguard is another agent using language model to check whether the code is safe. So in this case, it turns safe. The commander will finish that conversation with the safeguard and start executing the code. So here's the code execution result. It runs the optimization program with updated constraint and checks the new result. So the commander will then go back to the previous conversation with writer, send the execution result back to the writer. Here are the execution results. And after the writer sees that, it tries to come up with the final answer. This is a simple example of like using multiple agents and multiple steps to finish the task. In general, there can be all sorts of problems, like the code can be unsafe. In that case, the commander will not execute the code. And in case there's an execution error, the commander will return the execution error back to the writer, and the writer needs to rewrite the code. So in general, there can be multiple turns back and forth to finish the complex task. But here we're just showing one simplest case that is at a smooth trace. And you can tell how the end user now is able to still use a relatively simple user doesn't need to know there are multiple agents running at the backend. They just ask a simple question and then can answer in natural language back. The user doesn't need to understand any knowledge about the coding or optimization. So this is an example of using multiple agents. We allow the end user to achieve tasks that are much harder than before. Now, if you look at the programming perspective, how do they construct such a program? The way they do this is also very different from traditional programs. There are several steps. The first step is to create these several agents. So in this case, they're creating the writer, safeguard, commander, and user using one line for each. And then they need to define the interaction patterns among these agents. So here they registered 2 nested chats to the commander. For each nested chat, we need to define who are the agents involved in the chat, who are the sender, who are the receiver, and what's the summarization method from that conversation. And then their behavior patterns are defined this way. And finally, we just initiate the chat from the user proxy agent to the commander agent by sending the initial task requirement. And then every other steps also follow automatically. So the framework will handle all the steps and the nested chats and eventually return the result back. So hopefully that gives us an intuitive idea what the agentic programming means. And also, I'm using 2 slides to summarize the benefits. Number one is to enable us using these multiple agents to handle more complex tasks and improve the response quality for multiple reasons. You see that the multiple agents talking to each other can be a very natural way to make improvement over interactions. And we can divide and conquer a complex task to decompose that to smaller tasks and have more quality result for each step. And finally, we can define agents that are not necessarily depending on language models. We can have special purpose agents that perform grounding or validation using knowledge outside of the agent, not outside of the models, so that we can address the weakness inherent in the models. If you look at the chart on the right, this is an experiment result about if we decompose the task into 2 agents for the writer and safeguard versus if we put all the instructions in one single agent, how is the performance on the safeguard side? So if we compare the performance, we see that for GPT-4, the multi-agent setup has a 20% higher recall than single agent setup. And for GPT-3.5, the difference is even higher. So this indicates that for certain scenarios, it's beneficial to decompose the tasks and have agents to perform relatively simple tasks and compared to just asking the agent to do too much work in one try. And this is especially depending on the task complexity and the model capacity, right? So in general, the more complex the task and the weaker the model, there's a stronger need to have this multi-agent workflows. And another perspective is from the programming perspective. So in general, it's easier to understand, maintain, and extend the system if you have a modular design. For example, if you want to keep most of agents unchanged, but just change, for example, how you change the safeguard behavior, if you want to switch from using language model to using tools or using human, it's very easy to do that with modular design. And this allows natural human participation because human can take over any of the agent in the system. And by having natural conversation with other agents, there's no need to change how human interact with other agents. So combining these benefits, we see that the agentic programming has a promising potential to enable fast and creative experimentation and build novel applications. But it's not easy to design a framework that can meet all these promises. In general, we need to consider several factors to design such a framework. We want to have a unified agentic abstraction that can unify all these different types of entities. And we want to accommodate all the flexible needs for multi-agent orchestrations and satisfy all the different application needs. And we also need to make sure we have effective implementation of all the agentic design patterns. Let me use the next few slides to explain them. So first of all, for agentic abstraction, we want to unify the notion so that we don't need to have a hard time to reason about all these different type of entities, such as humans of different roles, tools, or language models from different providers. In general, these are all needed for building a common AI systems. But if we can have a single concept to think about them, it will greatly make it easier to reason about them. So let me explain more in the rest of the talk. One immediate benefit of that is now we can use multi-agent orchestration for building actually complex applications of common AI systems. And but to do that, we also need to think about all the different requirements of different AI agentic patterns of interactions. For example, sometimes the developer want a more static workflow so that they can clearly define each step and the order of the agents from the tasks. But in other cases, if it's hard to know all the possible situations that the agent need to handle, then we want to give the agents more autonomy and enable them to create more dynamic workflows. And similarly, sometimes they want to use natural language to tell the agents to perform the tasks, and at the other times, they want to use program language to have a more precise control. So there's a trade-off between the flexibility and the controllability. And there are many other trade-offs you could consider. For example, when do you share the context among the agents, and when do we isolate them, have a hierarchical setup, for example? And when do we want the agent to cooperate? When do we want them to compete to finish the task better? And there's also consideration about the centralized versus decentralized and automation versus intervention. So a good framework should be able to accommodate all these different requirements. And also, as people develop agents more and more, there are all sorts of like good design patterns emerging, and we need to also check whether a framework can meet all these design patterns requirements. There's a conversation. We want the agent to be able to deal with flexible conversations. There's also prompting and reasoning techniques like react, reflection, chain of thought, tree of thoughts, and so on. So there are more of such emerging reasoning techniques, including like Monte Carlo tree search-based methods. Tool using is a very important part of the agentic design patterns, and so is planning and integrating with multiple models, modalities, and memories. And it looks like a lot, right? So it's hard to have a framework that can consider all these different factors in the beginning. But if you think about this from the first order principle, you may wonder, like, is it possible to have a single kind of design point to start with and have all the other patterns to be able to, so that we can derive all the other patterns from that? So yeah, so can anyone think about among all these different design patterns, can you think of using just one single design pattern of them to accommodate all of the others? Yeah, I believe that different people will have maybe different ideas and started from the different parts. You may pick either one of them. So here I want to mention one personal kind of design point of view, that is a conversation. So this has a long time history. Back in college, I learned that conversation is a provable way of making progress in learning and prove theorems. And that's a takeaway. And when I see the power of ChatGPT, I immediately relate that back to my personal experience and decide, okay, so let's consider trying to use the multi-agent conversation as a central mechanism and see how far we can go. So it turns out we can go very far. So here I'm listing some examples of agentic AI frameworks, like AutoGen, and as I mentioned, is based on this multi-agent conversation programming. And it turns out to be very comprehensive and flexible. That's able to integrate with all the different design patterns I mentioned, and also other frameworks. And you will hear more from Jerry about LlamaIndex. And there are also some other like LangChain-based frameworks such as LangGraph and CrewAI. They focus on different, also starting reasoning points. Like LangGraph, for example, focuses on providing some graph-based control flows, and CrewAI focuses on providing some high-level static agent task workflows. Yeah, so that's a very brief overview of the Agentic AI frameworks in general. Next, I will go into the specific AutoGen. I will try to explain more about that. So AutoGen is a program framework for Agentic AI. It was initially developed inside another open source project called Flamo. Flamo is for automating machine learning and hyperparameter tuning. And later we spin off the standalone repo. And recently, we also created a standalone GitHub organization to have an open governance structure. So everyone is welcome to join and contribute. And here's a brief history about the journey. In early last year, we started prototyping these agentic frameworks. And initially, we just built a multi-agent conversation framework with the capability of code execution. And in August, we published the first version of the research paper. In October, we moved this repo to standalone GitHub repo, and it got a lot of recognition from the community. And such as this year, we got also a best paper at the Clear 2024 LLM Agents Workshop. And we're seeing more and more interesting use cases from the community, including both enterprise companies and startup companies. We just also offered an online course on deeplearning.ai about AI agent design patterns with AutoGen. So that's just very brief history about it. In general, AutoGen has very rich features about all the different AI design patterns. But today, I mainly want to focus on the most essential concept because this is a key to understand all the other patterns. So we wanted any developer to reason about a very complex workflow in simply two steps. The first step is to define the agents, and the second step is to get them to talk. So here we see two key concepts. One is a conversable agent, another is conversation program. So the agent concept in AutoGen is very generic, can abstract a lot of different entities. You can choose to use a language model as a backend for the agent, or you can use a tool or human input as a backend. And you can also mix multiple types of entities together. And furthermore, if you use this multi-agent conversation patterns, like you see on the right-hand side, you can build agents that can contain other agents inside it, have inner conversations, and then wrap them up as an interface to talk to other agents. So in this way, you can nest multiple chats inside an agent, have inner conversations, and build more and more complex agent in a recursive way. And the examples of conversation patterns include sequential chats, nested chat, and group chat. I will explain a few of them in the next few slides. The simplest one is a two-agent conversation. Even though this is a very simple conversation pattern, it already allows us to perform some advanced reasoning, such as reflection. For example, we can construct the writer for writing blog posts and another critique agent to make suggestions to the blog post. And you can have these two agents iterate and improve the quality of the blog post in this way. Now, if you think that's not good enough, you can add more other advanced reasoning techniques using this nested chat. For example, instead of using a single language model to do the critique, we can use a nested chat. And in the nested chat, we construct sequential chats that contain multiple steps of chats. We first send the message to the SEO reviewer, and then we send it to a legal reviewer, ethics reviewer, and so on. And finally, you can have a meta reviewer that summarizes all the reviewers' comments in different areas and gives the final comment. And from the writer's point of view, it's still talking to a single critic agent, but underneath a critic agent uses multiple other agents. So that's the idea how we can use a nested chat to potentially extend the agent capability using conversations. And think about tool using. How do we enable tool using conversations? Here's the example of building a game of conversational chess. We want the AI to be able to play the chess while chit-chatting with each other and making fun of each other. So if you just ask two language model agents to play the chess directly, they often make mistakes and form like random moves on the board which are not legal. So the game is not watchable at all. Now the solution can be that we can add a third agent called chessboard. This board agent is a tool-based agent. It uses some Python tools, Python library to manage the chessboard and provides the tools to other language model agents. So the language model agents can only make legal moves, and otherwise they need to be iteratively refine their moves until the moves are legal. In that way, we can make sure the game can carry on nicely. And again, we're using nested chat between a tool proposer agent using language model and a tool execution agent that's using tool as a backend, and having them talk to each other to finish that tool execution functionality. And there can be other more complex workflow patterns and solving more complex tasks using planning and using more dynamic way like group chat. In the group chat, the users only need to define agents of different roles and then can put them in a group chat, and they can automatically decide which agent to speak next, depending on the current progress of the task. There'll be a group chat manager which can monitor the progress and make the selection of the speakers. And furthermore, you could add more constraints or finite state machine translation logic about what orders should the agents follow. You don't have to make a very strict order. You can just give some candidates about like agent A. After agent A speaks, only agent B and C can speak, and not other agents, things like that. So there's still some decision made by the language model and some autonomy there, but you can add certain constraints to make sure at least the selection is within the scope. And you can further add some transition logic to tell the agent when you see certain situations, you should go this route, otherwise you go to the other parts. And you can use either natural language or programming language to specify that. Yeah, in general, there are many other type of conversation and applications enabled by these conversation patterns. Feel free to check our website for more notebook examples. They are nicely tagged, so you can search for anything question. For example, you can search for how to integrate AutoGen with LlamaIndex, and there are notebook examples like that. And in the paper, we just showed a few like very simple examples using simple conversation patterns. But in general, you can build many more complex tasks using these building blocks. I've seen developers building all kinds of sorts of complex tasks. So here's an overview of like the categories of domains that we are seeing from the community. The top two categories are software development and agent platforms. Coding, research, data processing, game the long tail. There's a web browsing tasks, finance, healthcare, education, and even blockchain, which is not shown in the list. Here I want to select a few interesting examples. The first one is in the science and engineering domain. This Professor Max Buller from MIT has done multiple work in different science domains, including protein design, material design, using AutoGen to build teams of agents that simulate the behavior of a scientific team or engineering team, all the way from like collecting the data, generating hypotheses, and then conduct experiments and verify the hypothesis. They have also built a very recent work called Sign Agents, which can use ontology knowledge graph to reason about any scientific domain and make interesting connections and do advanced reasoning using that knowledge graph. They construct a team of agents of multiple roles, and they can start from understanding ontology and then make multiple signs and critics to finish the very complex workflow including generate all the different concepts and possible hypotheses, and then select the best out of them. So this is a very promising use case. I see that in future has a potential to accelerate our science discovery, and maybe soon after we'll have some AI designed medicine or AI designed architectures and so on, or interesting alloys and materials. Here's another domain of web agents. This is an agent called Agent E, developed by a startup called Emergence.AI. They use AutoGen to build a hierarchical agent team so that they can perform some very complex tasks on the web, like automatically book flight tickets or automatically fill a form for medical clinics. This leverages some planning agent, some web browsing agent, and have some deep understanding of the content from HTML DOM. They haven't used any multimodal models, so they're only leveraging the HTML content and not leveraging the images and the vision models. But they already achieved the state-of-the-art performance on this Web Voyager benchmark, and now outperforms the previous techniques using multimodal models. There's still a large room for improvement. You can see the overall success rate is just 73%. So by combining multimodal models and the more agentic workflows, there's a potential to get it higher, even higher. But there's some very good foundational design principles we can learn from that work. And I also want to share a very recent quote I learned from a company doing construction. They're trying to use AutoGen to help the users without special knowledge or expert knowledge to be able to finish their construction projects. And they mentioned the benefit of AutoGen as being able to rapidly explore many different agentic design patterns, the configurations, and conducting experiments at scale. And that to summarize, we have seen big enterprise customer interest from pretty much every vertical domain, and got contributors or users from universities, organizations, or companies from all over the world, including some contributors from Berkeley. There's a work called MemGPT created by Berkeley students, and they also have integration of AutoGen. So very nice work. So we see that there's still a lot of changes and progress in AutoGen, and here are just a few examples in several categories, including evaluation, interface, learning, teaching, optimization. In the evaluation category, we're building agent-based evaluation tools to help developers understand how effective their application is, how good their agents are. It's a really difficult task because there are a lot of text generated, and it's hard to understand what exactly is going on. But using agents, they're able to automatically come up with success criteria based on the application and task, and then suggest the scores for each dimension. And furthermore, we can extend that idea to improve agents over time, right, by providing the feedback to the agents themselves and have agent-based optimizations or learning or teaching capabilities. One centerpiece of AutoGen is still to improve the programming interface to make it even easier for people to build all sorts of agentic applications. So I want to talk about one particular research that excites me. This is called AutoBuild. So one remaining question for many developers is, what is the most effective multi-agent workflow I should use? What agents should I create for my particular task? So AutoBuild is designed to address that issue as an initial attempt. So it works in this way. The user first provides a task to describe the high-level requirements, and the system will suggest agents of different roles automatically. And these agents can be put together in a group chat to solve the task. And for a new task, a more specific task, user task, we can reuse these created agent teams to solve that without the users need to specifically specify which agents to use. And we can further extend that idea from static agent team to adaptive agent team. So there's a technique called adaptive build. And in this case, we can first decompose a complex task into smaller steps. And then for each step, we propose a specific agent team for it. We can either choose from an existing library of agents or decide to create new agents that don't exist before. And after finishing one step, we now check what new agents do we need for the next step. So these agents can be dynamically selected. And as we create more agents, we can also add them back to the library to improve overall system over time. And we make experiments on several different benchmarks, including math, programming, data analytics, and so on, and find the very promising result that outperforms previous techniques of similar kind. Yeah, this is just one particular example of research we're doing. There are many more challenging questions. We still need the community to work on them together. The biggest question is how to design optimal multi-agent workflow for any application, and considering multiple factors like quality, the monetary cost, latency, and manual effort. In general, we still want to improve the agent capability from the reasoning, planning, multimodalities, or learning capabilities. And we also want to ensure like scalability and make sure human has a good way to guide their safety and so on. Yeah, so that's the end of my lecture. So I want to acknowledge all the open source contributors. And you can find our Discord community. We have a very large community on Discord, and find this new GitHub organization. And I'm happy to follow up with questions. Thank you very much.
Hey everyone, that was a great talk by Tree from AutoGen, and yeah, you know, I hope to build upon that. I think this is this talk is a bit less like generic, I guess, like in terms of the covering a lot of the different agent architectures and stuff. This is actually quite about like a specific use case around building a multimodal knowledge assistant. And so it's really focused on maybe some principles around like RAG and how do you actually extend that, building like a research agent. And it's like a use case that we've been exploring pretty deeply as a company. But of course, you know, there's plenty of agent stuff out there. You should definitely check out AutoGen, check out, you know, LlamaIndex, try building stuff on your own, and then see what we can come up with. So let's get started. And first, if you're not familiar with LlamaIndex, LlamaIndex is a company that helps any developer build context-augmented LLM applications from prototype to production. So we have an open source toolkit. The open source toolkit is a developer toolkit for building agents over your data. Well, different types of LLM applications. These days, there's a lot of people building, you know, agents. We started off helping people build like RAG systems, and now, you know, we're going into territories where people are building slightly more advanced stuff, where you're using LLMs for multi-step reasoning as opposed to just like single shot, you know, synthesis and prompt like generation. We also have an enterprise product, which I probably won't talk about too much today, but it's basically like a managed service to help you, you know, offload your data indexing and RAG and all that stuff. I'll talk a little bit about one specific piece of this, which is document parsing or, you know, data parsing. And we think this is like a pretty important piece in any sort of like context augmented pipeline. So let's get started. How many of you know what RAG is? Yes. So one part of RAG is you have a database. And so a database of some knowledge. And the way it works is you first want to do retrieval from that database to return basically just a bunch of text to chunk it. And then, you know, given the chunk context, embed it and put it into, for instance, a vector database. And we'll talk a little bit about that as well. So this overall goal of building a knowledge assistant is that, you know, a lot of companies have these types of use cases where they have like a lot of data. They have like 1 million PDFs. They have a bunch of PowerPoint presentations. They have Excel files. And you want to build some interface where you can take in some task as input and give back an output. That's really it. If you think about a chatbot, that's basically a chatbot. So you have a lot of data. You want your LLMs to basically understand that data, and then you want you know, the LLM to do stuff with that data. An example could be generating like a short answer. It could also be generating like a structured output, a research report. It could take actions for you, like send an email. It could schedule a calendar meeting, write code, do a lot of these things. We talk a lot about like RAG as a company, and especially if you're just getting started. If you follow like RAG 101 on how this works, we call that basic RAG. And so what is basic RAG? Basic RAG is you take like your unstructured data, you load it with some standard document parser, and then you chunk it into every 1,000 tokens or so. You just slice that text up into a bunch of slices, and then you stuff each slice into an embedding model, like OpenAI embeddings, and then you put it into a vector store. Then when you return stuff or you do retrieval from this database, you typically do semantic search or vector search to return the most relevant items from this knowledge base and stuff it into the LLM prompt window. This entire pipeline gives what I call like a basic RAG pipeline. It'll work kind of in being able to answer basic questions that you have over that data. However, there's a bunch of limitations. And the 4 limitations we list here is, one is the data processing layer is pretty primitive. When you do the chunking, you're not really doing or taking into account all the different elements within that data. You're not really taking into account, are there tables or images or weird sections, and you want to semantically preserve different chunks together. You're only using the LLM for synthesis, and so you're not using it for any sort of reasoning or planning. And so if you think about all of what like she just talked about with respect to agentic coordination and stuff, you're doing none of that with a basic RAG pipeline. And so it's kind of a waste of LLM capabilities, especially with the latest models like O1, 3.5, like Claude and whatever. Like a lot of these models have much greater capabilities than just being able to summarize over a piece of text. And so you want to figure out how do you actually use the model capabilities to do more advanced reasoning or planning. The other piece is, standard RAG pipelines are typically one shot, so they're not personalized. It's just like after you ask a question, it's going to forget about it. And so every new like interaction will basically be stateless. This has certain advantages, but if you're building a personalized knowledge assistant, ideally you're able to add like a memory layer to that. So a lot of what we asked ourselves is, can we do more than a basic RAG pipeline? There's a lot of like questions or tasks that a naive RAG pipeline can't give an answer to. This leads to hallucinations for the end user, like you doing like having a chatbot where it can't answer like 80% of the questions you might want to ask it is kind of like a limited value add. And so how do you build this more generalized knowledge assistant that can take in questions of like arbitrary complexity and answer that over arbitrary amounts of data? We think a better knowledge assistant has 4 main ingredients. And actually specifically the focus of this talk is on like how do you take in like a multimodal or build a multimodal knowledge assistant. So instead of just reasoning over like a standard text file, how do you reason over like an entire research report with a lot of diagrams and pictures, images? How do you like basically reason over all the visual data that exists on the internet in addition to just text? So the first piece is we need a core high quality multimodal retrieval pipeline. We want to then maybe generalize the output and think about something that's a little bit more complex than your standard chatbot response. So generating a research report, doing data analysis, taking actions. 3 is agentic reasoning over the inputs. So this is where, instead of just, taking in the user question and only using the LLM for synthesis, like applying chain of thought, tool use, reflection, all that fancy stuff, to try to break down the question, do some planning, and actually step-by-step work towards an overall goal. And last is deployment. We'll see how long I have. I plan to probably talk for 15, 20 more minutes. So just cover some of the high-level details. And for some of the actual like the examples, they're basically linked in the slides in case you want to check them out. The first piece is setting up a multimodal RAG. If you're familiar with RAG, you might be familiar with RAG over text data. But what we're really interested in is having RAG actually operate over just like visual data. And by visual data, I don't just mean like a JPEG file. I mean, even if your PowerPoint, for instance, like or like a research like archive paper, it's going to have like, charts, diagrams. It's going to have like weird layouts. And the issue with a lot of standard RAG pipelines is they do a terrible job at actually extracting out that information for you. And so like like I mentioned, any LLM or RAG or agent application is only as good as your data processing pipeline. And if you're familiar with the garbage in, garbage out principle in traditional machine learning, I think for LLM application development, it's no different. So you basically want to have good data quality as a necessary component of any production LLM app. This ETL layer for LLMs consists of basically you want to do some parsing from the document. You want to figure out a smart way to chunk it. And then you need a smart way to index it and put it into the LLM prompt window. This data source that I talked about, like this case study of complex documents, is a pretty common data format that we see across a lot of different companies. And so a lot of documents can be classified as complex, like embedded tables, charts, images. There's like irregular layouts. There's like headers and footers. And a lot of times, when you kind of apply like off-the-shelf components to parse a lot of this data, it ends up in a broken format, and the LLM hallucinates the answer. Users want to ask different types of questions over this data. So you have a bank of, like, say, PDFs. You want to ask questions over it. It could be simple pointed questions. It could be multi-document comparisons. It could be longer running, like, research tasks. A research task could be, given these 10 archive papers around LLM quantization or something, generate like a condensed summary or like a survey paper, right? And so that's something that's a bit longer or higher level in nature compared to something that's just a simple search and retrieval task. So we'll start with the basics, which is just parsing. Ideally, a document parser can actually structure this complex data for any downstream use case. I won't talk about it too much because the goal of this is really about agents, but really without needing to know the internals of like document parsing, you need to have like a good PDF parser basically. Because if you have a bad PDF parser, then you're going to load in some PowerPoint or PDF. It's going to not really extract out the right text from that PDF. And then when you feed in text that's been hallucinated by the parser, the LLM is going to have a really hard time understanding that, no matter how good the LLM is. So ideally, basically, you want a parser that can parse out like text chunks, tables, diagrams, all that stuff into like semantically consistent ways. That is one of the things that we do is we make a pretty good Gen AI powered PDF parser. We're at like 30,000 plus users right now. And yeah, I mean, if you're interested in trying it out, everybody gets like 1,000 credits for pages per day. And so it's used at different small companies to large enterprises. So you want to have a good parser, and what this enables is it's actually an important piece in being able to structure your data in the right way. If you think about different types of data, so here's like maybe like an investor slide deck, here's a 10K annual financial report, here's like an Excel sheet, here's a form. Having that parsing and extraction step to extract out stuff in the clean formatted data gives it's just much easier for LLMs and retrieval processes to understand that. Afterwards, once you've actually parsed out a PDF into its constituent elements in a good way, you can then leverage like hierarchical indexing and retrieval to do something more fancy than your standard RAG pipeline. So given this structure or document structure of like text chunks, tables, and diagrams, for each of these elements, a standard RAG pipeline will basically directly try to embed each of these chunks. But we found, for instance, a better approach is you actually extract out a bunch of different representations that point to the source chunk. So for instance, for a table, you might want to extract out a variety of different summaries that point to that table. For a picture, a picture you can't feed into a text embedding model anyways. And so you need to maybe use some model to extract out a variety of different summaries that point to that picture. For bigger text chunks, you might want to extract out like smaller text chunks that feed to that bigger text chunk. Once you extract out these representations, we call these nodes because these are the things that will be embedded and indexed by the vector database that you're using. So if you're using a vector database like Pinecone or whatnot, you can basically extract and index this metadata that is associated with the source element, but is not like the direct source element itself. Then during the retrieval process, given a user question, it'll first retrieve the nodes. And because the nodes have a reference to the source document, you can basically dereference it and then feed the resulting element into the model. notice that most models these days are multimodal in nature. If you look at O1, GPT-4o, Claude like 3.5 Sonnet, the latest Gemini models by Google, they can take in both text and images. And so the nice thing here is that you can still use text embedding models to represent the element itself. But then, like, when you actually feed stuff into the LLM, you're able to feed in both text and images. And so what I just outlined to is a basic way of of building a multimodal RAG pipeline. So a multimodal RAG pipeline can take in, any sort of document. It could have different types of visual elements in that document, and it will store both text and image chunks. And so in order to index the image chunks, you could use like clip embeddings, or you could do what I said, which is like, use a model to extract out text representations and link the text representation to the image chunk. And so when you set this up, then during retrieval, you feed in or you return both the text and the image chunks, and you feed both to a multimodal model. I'm going to skip this example, but here's like a basic example here that shows you how to build like a standard multimodal RAG pipeline. Notice up until now, haven't really talked about agents yet. This is just like setting up the basics of multimodal RAG. And so you don't get the benefits of like chain of thought or reasoning or tool use quite yet. All this is doing is saying, given a specific question you have about maybe a more complex data set, like research reports or slide decks, you're able to ask questions and get answers over, the visual elements on the page. So the next piece, actually, I might skip this just due to time. But basically, the high-level idea here is, a lot of the promise of agents is that it's not just going to give you back a response in the form of like a chat response, but actually generate entire like units of output for you. So producing like its own PowerPoint or PDF, or taking actions for you, or do you guys anybody use Claude like instead of ChatGPT? Anyone use Claude? You know how like when you ask it to write a paper for you for your Berkeley essay, then it'll actually generate like an entire thing on the side. That's an example of like report generation, right? It'll actually give you like a thing that you can just directly copy and paste into something that you then later edit. So for instance, like this is like a pretty common use case we're seeing in the enterprise too. So a lot of, consultants, like knowledge workers are interested in like basically like generalizing beyond the capabilities of just like giving you back an unformatted response, but giving you something that you can just directly use on its own. So whether that's code, whether that's like reports, it's all very interesting. And I'll probably skip some of the like architectures of how do you actually build this for now. And now we talk about agentic reasoning over your inputs. So this is a third section. So we have like, a multimodal RAG pipeline in place. Now let's add some layers of agentic reasoning to basically build agentic RAG. Naive RAG works well for pointed questions, but fails on more complex tasks. And again, this is due to all the reasons I mentioned above, right? You're just retrieving a fixed number of chunks. You're not really using the LLM to break down the question in the beginning. And so if you ask a question like summarization questions, where you need the entire document instead of just a set of chunks, comparison questions, where you actually need to look into 2 or 3 or more documents, multi-part questions, same thing, or a high-level task, you don't really get good results if you use a standard RAG pipeline. So there's a wide spectrum of different types of agentic applications you can build. And I think she probably gave much better architectures of like, how multi-agents can collaborate with each other and achieve very advanced things. The way we think about it is like, there's kind of both like simple to advanced agentic components. At the right, you basically have entire like generalized agent architectures, right? And so this includes like, a React loop, for instance, which is like one of the most common agent architectures these days, came out like about 2 years ago almost. And basically just uses some chain of thought plus tool use to basically give you some generic, agent architecture. You can plug in whatever tools you want, and it'll roughly try to reason over them to solve the task at hand. This also includes LLM compiler, right, which is Sehun's paper. And so this basically generalizes a little bit beyond React into doing some pre-planning, right? So instead of just planning the next step at a time, it'll actually plan out a DAG, optimize it, run it, and basically replan periodically. What we actually see a lot of people these days build is some people do use React. It's a pretty easy architecture to get started. But other people just like take some of the existing components and build more constrained architectures. And part of this is just due to the desire for reliability. Even though it's less expressive, even though it can't do everything, some people are still building up that trust towards AI. And so they're trying to solve a specific use case in the beginning. And so by solving this specific use case, they can leverage more specific components and try to maybe solve it in a more constrained fashion. This includes, by the way, like tool use, like maybe leveraging a memory module, like function calling we see at a lot of places. People are very interested in like structured output generation, tool use, being able to call like an existing API. And then also doing some basic like query decomposition, whether that is chain of thought or like parallel, like given a question, break it down into a bunch of different sub-questions. This overall thing we call Agentic RAG because it really is just like an agent layer on top of RAG. If you think about like RAG or retrieval or retrieval from a vector database as a tool, you can think about an agent that operates on top of these tools. So instead of like given a query, directly feeding it to the vector database, first passing it through this general agent reasoning layer, and this reasoning layer can decide to do a bunch of things to the query and also decide what tools to call in order to give back the right response. The end result is that you're able to build a more personalized QA system that can handle more complex questions. And this is an example of what I mean by unconstrained versus constrained flows. So for instance, a more constrained flow might just be, you have a task and you just have a simple router prompt. A router prompt is just a LLM prompt that just selects, one option out of n. And all it does is, given this task, feed the task to one of the downstream tools based on the decision in the router prompt, and then feed it to maybe like a reflection layer, and then give back a response. There's no loops in this orchestration. All that happens is it'll hit the router, go through a tool, go through another prompt that just reflects and tries to validate if it's correct, and then generates a response. This I defined as more constrained because a lot of the control flow is actually defined through humans, through you guys, versus through the agent. And typically the programs that are more constrained look like if-else statements and like while loops that you actually write instead of the agent. If you're using like a more generalized agent architecture, like if you're using like React or LLM compiler or tree of thought or whatever, then it's a little bit more general because you're basically saying, I don't actually know what the specific plan I want the agent to follow is. I'm just going to give the agent a bunch of tools and let it figure it out. And so this is more expressive because it can technically solve a greater variety of different tasks than you trying to hard code that flow beforehand, but it's also less reliable, right? It might veer off and call stuff like call tools that you really didn't want it to call. It might just get stuck in an infinite loop somewhere and never converge. And it's also more expensive. Typically, these types of agent architectures use bigger prompts. You're stuffing in more tools at once. And so the marginal token costs are much higher. And so we see a little bit fewer architectures being built with very wide unconstrained flows. But a good rule of thumb is if you're interested in using React or something, try to stuff in like 4 or 5 tools and try to limit it like to less than like 10 with the current model. We have core capabilities in LlamaIndex basically help you build workflows. So we call all of these things like workflows. They're basically all agentic in some nature. The very rough definition of an agent, everyone has a different definition. You guys might disagree with me. A very rough definition is just a program, like a computer program that has non-zero LLM calls. That's like a very general definition. And we basically help you write those types of programs. So whether you try to define a very constrained program where you're writing the if-else conditions or you're letting an agent handle that task, we basically have like an event-driven orchestration system where every step you can listen for a message, you can pass a message to a downstream step, you can pass messages back and forth between two different steps. And basically at a certain point, these steps can be just like regular Python code. They could be LLM calls. They could be anything you want. At a certain point, the program stops and it gives you back a response. And so we're building out this like very fundamental low-level orchestration because we believe that there's some like interesting properties among like agentic behavior where it is fundamentally a little bit event-driven. And this also provides like a nice base to help like users deploy workflows to production in the event that you want to translate your program into like a Python service. So check it out. I mean, I think I guess there are some links here, but this stuff is all linked in the docs. I'm gonna skip this piece and then, yeah. Some use cases that maybe are interesting to cover, which I think the links are basically here in case you want to check it out, is like we're very interested in like a report generation use case. So this is, again, something that we see pop up across a lot of different companies. And basically, given a bank of data, you want to actually produce some output from that data. An example architecture for this is you have like a researcher and a writer. And maybe like a reviewer as well. And you could think about this as like a multi-agent system, depends on how you define it. But basically you have like a researcher that does a little bit of RAG. It retrieves relevant chunks and documents from some database, and maybe like given a task, like make sure that it's like going on the internet and fetching stuff, like and storing it in your notes. It'll put that stuff in a data cache. Like basically this contains all the relevant information you need to generate the report. The second step is like a writer. And this writer might use this data cache to then make like an LLM call that will then generate this interleaving sequence of like text, image blocks, tables, and give you back a full output. So we have an example architecture here, and we also have some example repos where you generate like an entire slide deck instead of just a report. Another use case, by the way, which isn't in these slides but is very interesting, is customer support. I think if you look at just practical enterprise use cases of agents, customer support for external facing use cases is probably number one. This is, basically like there's like just a lot of automation that could be baked into the decision flow to basically increase your deflection rate and basically ensure that the user ends up having like a much better experience than going through like those automated phone menus. And so we see that popping up in a lot of different places too. And then the last bit is really around running agents in production. I think, so far, if you start off like building a lot of these components, you're probably going to start off in like a Jupyter notebook. And that's totally fine. When you start off building a prototype, it makes sense to do something that's very local, that's very narrowly scoped, and you basically see if it works over test data. An interesting design exercise is to think about what a like complex multi-agent architecture looks like and how we can leverage like existing production infrastructure components to like achieve that vision of like multi-agents in production. Ideally, if you think about agent 1, agent 2, agent 3, every agent is responsible for solving some task, and they can all communicate with each other in some way. So you ideally can encapsulate their behavior behind some API interface, and then you can standardize the way they communicate with each other through some sort of core messaging layer. You can easily scale up the number of agents in this overall system to add more to this like multi-agent network. And you can also take into account a large volume of client requests with different sessions. So this is basically what we're building, and it's like a work in progress, but we've made a lot of progress in the past few months. Is like how do you actually deploy agentic workflows as microservices in production? So you model every agent workflow as like a service API. We allow you to spin this up locally and also deploy this on, for instance, like Kubernetes. All agent communication happens via like a central message queue. You can have like human in the loop as a service. So for instance, like, if like this agent actually needs your input, it will send a message back to you, await your response, and then you give it, an input before it resumes execution. How many of you have seen like the Devin demo, like the Cognition Labs Devin, you know what I'm talking about? How many of you know what like Devin is? All right, so like half of you. I think if you took a look at the demo, one example that does is like this coding agent will just generate an entire repository for you. But sometimes it will stop, right? Sometimes it will say, I don't actually have enough clarity to basically kind of give you the response. Can you actually tell me what to do next? And so if you played around with Devin, that's basically what it does. And that's an example of the human in the loop. This like kind of interesting back and forth like client server communication where the server is actually waiting on the client to send like a human feedback message. So that's basically it. All these components, I think, are kind of like step by step towards this idea of building a production grade multimodal knowledge system over your data. And yeah, thanks.